All right, so let's take a look at our, as you guessed it, 4-step plan for hypothesis testing for a population mean. We'll be a little more formal here. Should CV switch to bottled water? We saw that question before, so now in the detailed approach, we'll recall that a mean lead level of 15 parts per billion is considered safe, while anything above 15 parts per billion is considered dangerous. Mr. High believes the CV water is unsafe, so he takes a random sample of 200 households. He finds the average lead level of the sample to be 16.5 parts per billion with a standard deviation of 8 parts per billion. All right, so as we establish our 4 steps here, state the parameter. Well, we're testing the mean, true population mean lead level for houses in CV. Our statistic is our sample mean of 16.5. Our hypotheses, null hypothesis is that the mean is equal to 15. If it's less than 15, no worries, that's great. Anything that's no more than 15 is considered safe. So this is a one-sided test because we're really only concerned about the mean being more than 15. And our significance level we'll use here, we'll go with our 0.05. If nothing is stated, we'll just default to this value. That's a common percent to use for significance level. The plan step, now that we have a new type of test, we have a new name for it. So in our proportions test, we called it a one sample Z test for P proportion. We just need to make 2 little letter changes. This is now a one sample T test for mu, the population mean. Make sure to name correctly so we know what test, this basically says what test stat you're getting and what parameter you are working with. Our conditions. What says that Mr. High took a random sample of 200. So we have the random condition met. Normal. Well, our sample size was 200. That is at least 30. So the central limit theorem's got us covered. Our sampling distribution of samples of size 200 will produce a normal distribution of those sample means. Doesn't matter if the original population was skewed or had outliers. We're covered. So that was the easy type. Do, well, the mean of our sampling distribution, the mean of those sample means will be the mean of what we assume to be of 15. We start with that assumption. Our standard deviation of the sampling distribution would be the standard deviation of the sample divided by the square root of the sample size. So we had a standard deviation of 8 from the problem for the sample of 200. Divide by square root 200 to give us a standard deviation of the sampling distribution to be 0.566. So that tells us that samples of size 200 will typically vary by 0.566 parts per billion from a mean of 15 parts per billion. Here's my picture. So 15 is the mean. Our sample value was 16.5. I shaded the area to the right. That would correspond then to the p-value. Continuing on in my do step, my formula here to calculate my test stat, my t-star value. Sample minus the null, divide by the sampling standard deviation of the sampling distribution. There's the value. Now here's an example of one where we're going to have to be careful. When I go to use the table, a sample of 200 would have a degrees of freedom of 199. I'm going to have to use 100 here because, let me get my table, as you can see, 199 is not an option. We start to make jumps here. Once you hit 30, 40, 50, we go by 10s and then eventually 20s, and then we jump all the way from 100 to 1,000. So when you have a number that is, in this case, 199, always go down to the next one. So if I had a, say for instance, a degrees of freedom to be 99, I know that's close to 100, but err on the side of caution and always go down, so we would go all the way back to 80. It's not the closest one that we go to. You need at least that number to feel comfortable with the p-value that it would produce. So since you don't have at least that number, always go down. I don't have at least 199, so I'm going down to 100. And then remember our test stat value was 2.650. So I'm going across this row, 2.650. Let's see here. Looks like I'm in between these two numbers. So I go up to the top of the table, and that says our p-value is probably between 0.01 and 0.005. And this was a one-sided test. Oh, did I use the wrong one there? I wrote the different number. Let me go back to the table again. Was that degrees freedom 100? What did I say that was? 2.65. I mixed those numbers up in my head. My mistake, guys. Maybe you caught me on that. So pat on the back if you did. It was 2.65, and that would be between these two instead. So now I'll slide up to the top of the table, and there we go. The p-value is between 0.0025 and 0.005. There, we got it. So that value, whatever it happens to be, is definitely less than or equal. Actually, I should just strictly say less than. I don't know why I put the equals in there. So 0.0025 in between these two is definitely less than our significance level. So we are going to go ahead and reject the null. We have convincing evidence that the lead levels are above 15 parts per billion and CV should switch to bottled water. So that was our 4-step plan there.